So in the earlier videos, we were talking about how to do the Lewis structures, and that's where you take the atom fragments and you figure out what kind of different bonds could get formed. All right. There's a couple of good things about these structures that you can draw, but they also have their limitations. All right. And in this video, we're going to talk about molecule shapes. All right. So the thing about drawing the Lewis structures is, and I've given an example of one right here. We've got a carbon with 4 hydrogens drawn to it. The problem is that by the nature of doing that, you're drawing things on a piece of paper or you're doing it on your computer screen, and that only, at least when you're doing it, freehand, this only allows for a 2-dimensional representation. All right, and the reality about molecules is that most of them are, well, all of them are actually 3-dimensional. All right, some of them will be flat, but some of them are not flat. All right, and that presents a problem with how you draw these things. All right, so I like to use the analogy that drawing a structure like this is kind of like representing a human like this. All right, it's not like these things are useless. All right, if I was to show you a stick figure, does it correctly communicate that a human has 1 head, 2 legs, 2 arms, and so on? Yeah, we can figure out the number of body parts by looking at this representation. We also know a little bit about where things are connected. For example, you could tell that the arms are connected between the head and the legs. All right, so this representation right here does the same type of thing. I can tell that there's 1 carbon that has 4 separate hydrogens connected to it. All right, but where's the limitation? All right, the thing is, it would be impossible to show any 3-dimensional aspect of the human body with a simple stick figure. All right, because it's drawn on a flat piece of paper. All right, the best you can do on paper is create the illusion of 3 dimensions, but we can't really go any farther than that. All right, so what are the true shapes of these molecules? All right, the theory that determines that is this thing called VSEPR. All right, and even though it's VSEPR, you pronounce it VSEPR. All right, that stands for valence shell electron pair repulsion theory. All right, it sounds like a mouthful, but it's actually not that difficult of a concept. All right, all that this says is that the electron pair clouds like to repel each other. They don't like each other, and when things don't like each other, they try to get as far apart as they can. All right, so to give an illustration of this, I'm going to start with this molecule right here. All right, this is actually ammonia. You might recognize that from a chemical that's in window cleaner. All right, so it's got 3 single bonds to a hydrogen, but then it's got this lone pair right here. All right, so this is a representation, but remember what these bonds are. All right, these bonds represent, each of them represent 2 electrons, all right, or a pair of electrons. And you can think about that, you can think about this right here as these 2 electrons. It's basically forming a cloud that, in that cloud, so I'm going to represent that here. You've got a cloud, and what that cloud is actually just 2 electrons, all right? And picture this electron right here, but it's just spinning its time going between these 2 molecules. So it surrounds, or sorry, these 2 atoms. So it spends its time surrounding both of these atoms right here. Same thing with this electron right here. And it's going to spend its time surrounding, flying around these 2 atoms, all right? But if things start to move fast enough, all right, hopefully you realize that once that little dot is going fast enough and your eyes can't see it individually, it starts to look like a big blur. All right, if you ever try looking at like a bicycle tire, all right, with the spokes, when the wheels are going really fast, you can't really see the individual spokes. All right, you just kind of see this blur. All right, so that's what they mean by cloud. All right, so this bond right here would be 2 electrons circling these atoms. Same thing here. Same thing between these atoms right here. But notice also that there's this lone pair. And a way that you can think of that lone pair is that it's just another cloud made up of 2 electrons. And the only difference is at the end of this cloud, we have an atom, but there's no atom at the end of this cloud right here. But it still juts out into space, and it has the same issue of all the other clouds. And that is that the cloud has a negatively charged surface, all right? And that's because it's comprised of electrons, which are negatively charged. So this is going to be a negatively charged surface. Same here, and same here, all right? And all this theory says is that these clouds don't really like each other, all right? They repel because they have like charges, and that causes them to want to get as far away from each other as possible, all right? And what ends up happening is that when you have certain numbers of these electron clouds, it ends up creating certain types of shapes. All right, and so that's what we're going to talk about here is the types of shapes that you would encounter. So one thing that can make this theory a little bit confusing is the fact that even though these electron clouds, the electron pairs or the lone pairs, such as this right here, even though they affect the shape of molecules, they're not included in the shape of the overall molecule. The overall molecule shape refers only to the position of the atoms. All right, so hopefully that will make more sense when you see examples of molecules that have lone pairs in them. All right, another important thing to remember is that double and triple bonds don't count as multiple different bonds. All right, when you're counting how many clouds this molecule has, for example, this double bond right here should be considered as one cloud that happens to contain 4 electrons instead of 2 separate clouds, each containing 2. All right. Another example, this has got a triple bond right here. So this triple bond should be considered a single electron cloud that has 2, 4, 6 electrons in it. All right. And this cloud would want to repel this cloud right here. And the only difference is that this cloud right here only contains 2 electrons. All right, so that's actually a common mistake that people make when they're doing this, is they consider something like this to be 3 separate clouds when it's only considered 1 cloud. All right. So to help with figuring out the shapes of molecules, I've provided this little chart that will help you to determine the shape, and you'll see how it's used in just a second. The first shape I'm going to go over, though, is not even on this chart right here. It's the simplest of all shapes, and it should be common sense, and that's whenever you have 2 atoms that are just 2 atoms that are bound to each other. All right, and the only possible shape that this can have is a straight line. All right, so it gets a little bit more complicated when you start to have central atoms, and so let's see some examples of those. All right, so the way to use this chart, in this first column right here, think of this as the number of clouds that are coming off of a central atom. All right, and remember we were talking about what defines a cloud. A cloud can either be a single bond, it can be a double bond, it can be a triple bond, or it can be a lone pair. Because remember, a lone pair can be thought of as just a cloud, but there's no atom at the end here. All right, so the second column right here, you can think of that as where it says number of atoms coming off. The number of atoms coming off the central atom, that's literally the number of atoms that are bound to that central atom. All right, we'll talk about the difference between parent shape and the what you would see shape in just a second. But to give you an example of this, let's consider this molecule right here. All right, let's count all of the clouds that are coming off this central atom right here. All right, so remember to consider a double bond to be a single, just a single cloud here containing 4 electrons. Think of this double bond the same way. All right, so that is 2 clouds. All right, and the second question you have to ask is, how many atoms are bound to that central atom. All right, there's two. This is an atom right here, and this is an atom right here. The only thing that doesn't count as an atom is going to be a lone pair. All right, so a lone pair counts as a cloud, but it doesn't count as an atom. So this would be two atoms. All right, and so using the chart here, what it says is that the parent shape would be linear triatomic, and what you would see shape would be linear triatomic. And all this basically means is that this would be, the shape of this would be a straight line. Meaning that literally the shape you would have in going from this oxygen to this carbon to this oxygen is a straight line. So that would be 180 degrees from this bond right here to this bond right here. Right. And I just want to point one thing about that name. The triatomic part comes from the fact that there are just 3 atoms in that arrangement. So the next example I've shown right here. All right, so in this example, let me switch pen colors. All right, in terms of number of clouds, we have a cloud here. All right, we have a cloud right here. And each of these clouds would have 2 electrons in them each. All right, but then we have this cloud here, the double bond. All right, and that's a cloud. It's just that it's got 4 electrons in that cloud rather than these, which each have 2. All right, so here you have 3 clouds. All right, but you have 3 atoms. All right, at the end of each of these clouds, there's a hydrogen atom, that's a hydrogen atom, that's an oxygen atom. So if you look here at the chart, 3, so 3 clouds, and 3 of those are atoms. This is what you would call trigonal planar. Okay, and the best way to describe it is the letter Y. All right, literally, if you took the letter Y, it's the angles between these are all the same. All right, it's going to be 120-degree angles between all of those. And the other thing about the letter Y is it's flat. All right, literally, it would lay flat. Every part of it lays flat against the paper that it's drawn on. All right, you'll see examples of things where that's not true in just a second. And hopefully so far these shapes make sense. All right, if you just asked yourself, if you had 2 clouds connected to the central atom, what shape allows things to get, 2 things to get as far away from as possible? All right, that would be a straight line. All right, well, what lets 3 things get as far away from each other as possible? That would be kind of like a Y shape. All right, so moving on to the next one, let's consider this molecule right here. All right. And the question is, so if you just looked at this right here, your first impression might be it's going to be a straight line, because here we had 3 atoms in a row. We have 3 atoms in a row here, all right? But we need to consider the contribution of the central of this lone pair here. So remember, what you actually have is you have an electron cloud coming out here. You have a cloud here that contains 4 electrons, and then a cloud here. All right, so this is where we come to the difference between a parent shape and a what you would see shape. All right, so these 3 different groups would all want to get as far away from each other as possible, which would make like a letter Y, just like we had here, which is Y shaped. But you have to ask yourself, the thing that you have to remember is that the shape of the molecule is only they're only talking about where the atoms are. And you only have atoms here, here, and here. All right, there is no atom at the end of this lone pair, even though it does have an effect on the shape. All right, so if you just consider what would be the shape of just this, this, and this, that would be sort of like a boomerang shape. All right, and what we call that shape is bent triatomic. All right, and I always just use the analogy that's kind of like a boomerang. All right, it's going to have a little bit of a bend to it. And what gives it that bend, so why is it that this thing doesn't want to be in a straight line